Hi everyone, and welcome to a new session. Today I'm talking to Ángel González Prieto, and we're going to be discussing his paper called Optimization of Algebraic Invariants through Quantum Field Theories. It's going to be a very mathematical discussion, but if you enjoy that, then I think it'll be very interesting. Let's jump into it. Ángel, thank you very much for joining.
Thank you very much for inviting me to be here. I'm super happy to have at the time to talk to you about these kind of things.
Wonderful. As we made clear just before starting the recording, we're going to start from a high level now and try to make our way down into the details that you're focusing on. We have the paper on the screen now. It's called Quantization of Algebraic Invariants through Topological Quantum Field Theories. I think the natural place to start would be to just introduce quantum field theories to begin with, and then topological quantum field theories in particular. Would you mind just giving a quick overview to quantum field theories first, and then we'll focus on the topological variants?
Sure. So the idea, well, first of all, a disclaimer: I'm not a physicist, so I can explain the way a mathematician thinks about quantum field theory. So the idea is, quantum field theory is a way of understanding how quantum fields. So you have a classical field structure like electromagnetism, and you know that this classical picture is not accurate enough to capture some kind of phenomenon occurring in the nature. So you want to promote your classical field theory into a quantum field theory. So you quantize your vector fields. And typically this corresponds to, okay, I have some space of vector fields, of some space of fields that is typically something related to classical calculus, and you replace this space of fields by a Hilbert space, a vector space with some additional data. And in this Hilbert space, you apply quantum mechanics. That's cool. That's the classical picture of quantum mechanics. But now you want to understand how these quantum fields, how these quantized vector fields behave when you change the geometry of your underlying place in which you are understanding the physics. For instance, you are in a particular moment of the universe and you want to evolve from this particular moment to another different moment, and you want to understand what is going on with your quantum fields, how they evolve when you move in the universe. And that's the idea of quantum field theory. It develops a way of understanding how the vector fields that you have, the quantized vector fields that you have in a very particular moment of time, evolve when you change to another moment of time. So that's the idea of quantum field theories. And the way they do that, physicists, is through a device known as a path integral. So the idea is they say, okay, I have my vector field here on the initial state, and I want to understand what is the final possible state. So I will check what are the possible paths in which this vector field can evolve into the final state. And this is an infinite number of paths. They do some kind of integral, and at the end, using this integral, they manage to get what is the final quantized vector field that they get. The problem is that this path integral is ill-defined. So it's not well-defined at all in many cases, because it's an integral in an infinite dimensional space. So there is no...
How come infinite dimensional?
Super large. I mean, it's not clear at all that it has a natural way of measuring there. So for instance, it's like all the possible... So a typical way will be to think all the possible vector fields interpolating between my two vector fields in the initial state and in the final state. So it's a super big space. It's infinite dimensional. There is no natural notion of how to measure things then, how to integrate there. So you need to do something. And physicists have developed some kind of tricks to understand what is going on in some very particular cases. Like, for instance, they say, I have this integral, and they say, okay, even though this integral has a contribution of infinitely many paths, there are some paths that are more prominent in this integral, and these are the paths that contribute the most to the final result. So instead of taking this infinite sum, which is the integral, I will take a finite sum, truncated finite sum through this typical path. And the idea is, I can explain this very easily. Suppose that you have a bag on top of a mountain, and you want to, this is the classical picture. You have a classical field, the classical gravitational field of a bag on top of a mountain, and you want to look at what happens when the bag is at the bottom of the mountain. And you say, okay, classically, there will be only one possible path, which is the shortest path, the shortest way of going from the peak of the mountain to the valley. That's right. But quantumly, you can take different paths, because you may say, okay, it's not super possible that I will do that, but there is a small possibility that I decide to move around the mountain, and at the end I reach the top of the bottom of the mountain. That could be a possibility. This typically happens, for instance, in some cases in which you put a wall of potential, so that you have an electron that will not be able to cross this wall of potential. But even though classically it's not possible to cross this wall of potential, quantumly it's able. There is a small possibility of crossing, and this is called tunneling effect, quantum tunnel effect. So that's the idea.
Yes.
In the quantum setting, every possible path contributes to the final result, even though it's not the classical path that you will take. But what happens in this integral, there are paths that have more probability than others, and you say, okay, I will approximate my result by considering only the paths that are more likely to take, and that's the idea.
And in the analogy that you painted with the mountain and the bag, the bag would correspond then to an entire field, or are we solely talking about excitations in the field? So to give some more context, my understanding is in quantum field theory, you would represent particles that you would normally have in a classical setting with excitations in these fields. So you get rid of the particle notion in that sense, but it's purely an excitation of whatever field you're considering. And when we're then talking about path integrating these with respect to something, whether it be, I don't know if time is one of these parameters that you could integrate over, but time tends to be quite problematic, so maybe space in some sense. As you're doing that integral, what you're really considering, is that the full field that you're integrating over, or is that an excitation in the field that you're sort of cutting out?
So the point is that you are integrating along all the possible fields, all the possible excited states that interpolate between my current state and the final state. And I'm integrating through all these possible states. And this is the super infinite dimensional space in which I have to integrate. So
okay, do you always have the final state in that kind of analysis? So you're saying now that you're interpolating between these 2 points, but let's say you're trying to use the theory to predict some form of result. I would guess that you don't have the final state, but you would actually want to get to that. Is that a like very different kind of application of the theory that we're not concerned in this particular area of research now, or is it? Am I missing something?
So the point is that theoretically you should be able to say, okay, if I have an initial state here, when my time evolves, my universe evolves, I end up with this state here. And that will be the ideal situation, to say, okay, there is a map that says this initial state ends in this final state. And that's the kind of things that you would expect. Physicists say that, okay, you can do this. There are some techniques to do these calculations. But the important point for a mathematician is that instead of keep thinking about this physical intuition behind these ideas, you say, okay, I will keep the mathematical idea. And the mathematical idea, you distillate the mathematical idea behind this construction. And the mathematical idea is very simple. Is, okay, to every possible universe, so to every possible manifold, to every possible topological space with some particular structure, I'm able to construct a Hilbert space, a vector space. So this is the first ingredient in this recipe, to be able to assign to every possible manifold, to every possible initial state of your universe, you assign a vector space, the Hilbert space that will quantize this physical system. And whenever you have an evolution, and an evolution in topological terms is a Bordism. So a Bordism is a manifold, a higher dimensional manifold that has boundary, and the boundary of this manifold are precisely the initial state of the universe and the final state of the universe. So you have this Bordism.
Okay, can I pause you there for a second just to introduce these two terms as well in
Sure,
a bit
sure,
more
sure.
detail? So I think manifold, if we start there, because I think that's a really a cornerstone of the research, and it's something I haven't discussed before. So would you mind describing manifold? My understanding of that at the moment is it's sort of a generalization of a surface that we would consider or some form of geometry in classical space. Would you mind painting some more picture as to what it means when we're talking about manifold?
Sure. So a manifold is, as you say very well, is a generalization of the idea of surface. So the idea is a manifold is any possible space that, even though the geometry of this space is super complicated, locally it looks like an affine space, like the typical space, Euclidean space we are used to. So in particular, the typical example will be a sphere. A sphere, a two-dimensional sphere, is something that globally is not like an Euclidean space, because globally is something that is round. But if you look with a magnifying length around a particular point, you get a patch, and this patch is actually like a Euclidean space. So these are the spaces that typically geometers are concerned with, because are spaces that, even though globally the geometry is very complicated, like spheres, or for instance torus is like a donut. So spaces like this that globally have a very complicated structure, locally they look like an Euclidean space. So it's like, okay, I have, like, the typical example is what happens with the maps that you have when you are navigating the sea. When you are navigating the sea in the sphere, in the Earth, what happens is that, even though the global geometry is complicated, you have a map that says you are here and you can move to here. So even though globally you cannot understand the whole space, you can say, okay, locally I have a map and I can apply typical techniques from calculus to understand these spaces.
Okay, so it's essentially, in layman's terms, I guess, a space that you can linearize close to the point that you're actually standing at, let's say.
Exactly.
Okay, and how does that relate to the concept of quantum field theories now? Why is it necessary to make this generalization of surfaces that we're normally considering to this? Does it help with simplifying, let's say, the path integrals that we have, given that we can then locally consider them as Euclidean spaces as opposed to something more complex, or what's the purpose?
So the idea is that, what is the universe? The universe is something that is four-dimensional, because there are four dimensions, three spatial dimensions and one time dimension. So our universe, our state, is something that is four-dimensional. It's some four-dimensional, super complicated object that locally looks like the Euclidean space times time. So
Hmm.
uh, even though the possible geometry of the universe is unknown and is very complicated, locally it looks like, okay, I have the corner of my room and I have time, and these are all the possible quantities that I have. Okay, this is locally in a short space of in a short patch. This is true, but in large scales this might not be true. So the idea is,
Hmm.
okay, you need to understand these manifolds, these very complicated geometric spaces that locally look like a Euclidean space, because it's where physics take place. And this was the brilliant idea of Einstein. Einstein was the first one that realized, okay, we have to understand space-time not as something as simple as R4. So for real numbers, we have to understand space-time as something much more complicated, as some kind of geometric object that locally looks like this, but globally may have a different geometry.
Hmm. Okay, so how does that then relate, to get back to what we were talking about before, to Bordisms now?
Okay, so the idea is I have my universe, I have my state. I'm thinking about universe because it's the easiest way you can think about this, but typically you could also say, okay, instead of modeling the whole universe, I want to model this physical system, like a pendulum. I want to model a pendulum. And for instance, what is the possible states of a pendulum? Well, you have a pendulum, and the pendulum, the information that you need to know to understand where is the pendulum is what is the position of the mass at the end of the pendulum, and what is the velocity of this mass. So there are two quantities to understand: the position of the mass in my pendulum and the velocity of this mass. So the manifold associated to this mechanical system, the manifold associated to this classical system that you want to quantize, will be a two-dimensional manifold, a surface. A surface that has one coordinate, which is the angle of the mass, and another coordinate that will be the velocity of my mass. And with these two quantities, I understand perfectly the motion of this classical object. So my initial state will be this two-dimensional manifold, this pendulum. And now I do something to my pendulum, so I add some mass at the end or whatever, and at the end of the day, I end up with a different system. For instance, suppose that I add to my initial pendulum another pendulum like this, so that I get a double pendulum. Now I have the double of the quantities, so I have two possible positions: the angle of the first mass and the angle of the second mass, and I have two velocities. So instead of getting one surface, at the end I get two surfaces. Okay, and I have this perfect, and I have and now I want to say, okay, how did I evolve from this initial state to this final state? Well, I evolved through a Bordism. And what is a Bordism? In this case, I had some surface here and some surface at the end. And what is the evolution between them? An evolution will be like a movie of surfaces interpolating between the initial surface and the final surface. So it will be like a three-dimensional manifold, a three-dimensional space, such that the boundary of this three-dimensional space are the initial and final surfaces corresponding to the possible states of my mechanical system. So that will be the idea.
Okay, so one part I didn't quite understand with that was when we introduced the double pendulum. So in the first case, it makes perfect sense. We have a single pendulum. We have two coordinates that are necessary to characterize the system, and hence the space, let's say, of possible states that we could be in will take the form of a two-dimensional plane, let's say, or a surface, a two-dimensional manifold. When we now introduce a second pendulum, I wouldn't describe that as two surfaces because that would somehow imply that these two are independent. And I guess they're not. Specifically, the first pendulum, well, and the second pendulum would be interdependent, I would suppose. How come this is not represented? You said it's represented as two surfaces or two-dimensional manifolds. How come it's not one four-dimensional manifold according to the same logic as in the first example?
Actually, you're right. I was lying. I was trying to oversimplify.
Okay.
I was trying to oversimplify the picture, but that's a fair point. You're right. A double pendulum is not two-dimensional manifolds. It's actually a four-dimensional manifold. What I'm trying to say is, okay, let's change the idea of, instead of considering that I have one pendulum, suppose that I have one pendulum and at the end I have two different. So I'm doing something to my pendulum. The problem is that it's not that simple in reality. But what happens is, okay, I have my mechanical system, and suppose that I have this mechanical system and this mechanical system, I can split it into two possible mechanical systems. So I have, at the end of the day, I have two possible pendulums, and I have two possible pendulums that are independent. So it's like I have, I can either end in this kind of pendulum or in this other kind of pendulum. That will be kind of the idea. So I'm splitting my pendulum into two pendulums. You're right. A double pendulum has as phase space a four-dimensional manifold. That's right. What is going on is that I'm splitting my pendulum in two possible pendulums, actually.
Okay, so it's like the superposition concept in quantum mechanics.
Exactly.
You have some system, it can end up in one or two states. You want to figure out which one, and then the introduction of the extra dimension that you mentioned in the Bordism is sort of the way that you traverse from this original one to either of the final states? Is that the...
Exactly.
Okay.
So it's like when you are evolving, at every possible time, you fix the time, and when you fix the time, what you get is another mechanical system. So you get a surface, but you are interpolating from the initial surface to the final surface. And this is the Bordism.
Mm-hmm.
Okay?
Mm-hmm.
So that
Okay.
will be roughly speaking, the idea of this geometric picture. And this will be the classical geometric picture. I have a mechanical surface, system, a surface. I have another mechanical system, another surface, and I have an evolution in time between them. Cool.
Mm-hmm.
Now what is going on when I want to pass to the quantum world? When I want to pass to the quantum world, my rule says first, to the initial surface, the initial classical system, I have to assign a Hilbert space. I have to assign a
Mm-hmm.
vector space with an inner product. And that,
Mm-hmm.
so, okay, I apply classical techniques from quantum mechanics to quantize my mechanical system into a vector space. Cool. I do the same with the final mechanical system that were two pendulums. I quantize them, and then I get another Hilbert space. Cool.
Mm-hmm. Just one question on that as well. If we talk about this from a mathematical perspective now, is that always possible? Like, if we're talking about physical systems, I guess it's always possible to quantize them, given that we assume that the world is fundamentally quantum at some level. But if we're talking about this mathematically, are there constructs that you can create where it's not possible to introduce a Hilbert space on top of it?
That's a very good question. Quantizing something is not. I have explained this as, okay, there is a recipe that tells you how to quantize, but it's not that simple at all. What happens is that,
Mm-hmm.
first of all, it's not clear. First of all, it's not possible to quantize every possible space. And the second point is that even though you can quantize it, you can quantize it in different ways.
Okay.
So it's not a one-to-one correspondence. It's true that there
Mm-hmm.
exists some rules, heuristic rules that physicists apply to quantize stuff, but it's true that, okay, for some particular mechanical system, they apply these rules. But what happens is that you can quantize in different ways. For instance, what happens is, if your equation of motions depend on, let's say, two possible quantities that are multiplied, okay, you will say, okay, I'm replacing this quantity by its quantum operator. I'm replacing this quantity by its quantum operator. Cool. But the problem is that quantum operators do not commute. So even though classically I have, let's say, x times y, and I'm substituting x by the quantum counterpart, and I'm substituting y by the quantum counterpart, it's not clear if I have to say x quantum times y quantum or y quantum times x quantum, and both of them are different. So it's not that simple. Actually, quantizing in general is an open problem. Probably is an unsolvable problem. But there are some particular cases, some very controlled cases, in which there exists a mathematically rigorous way of quantizing. And this is, for instance, known as geometric quantization. Geometric quantization
Okay.
is a technique that gives you a manifold with some extra structure, and with this manifold with this extra structure, you are able to construct one single Hilbert space associated to it, and in a functorial way, in a well-defined way.
Mm-hmm.
So
Okay, thank you very much for the explanation. Yeah.
So that will be the idea. Okay, I'm doing this quantization, applying some kind of technique. So, for instance, we can think that we are considering mechanical systems to which I can apply geometric quantization. So I'm quantizing this mechanical system into a Hilbert space, the other one into a different Hilbert space. Cool. And now I want to add the dynamical point of view to the picture. So I want to know, okay, if my system was in this quantum state, where is this system going to end after the evolution? It's going to end here, it's going to end here, it's going to end into a superposition of states, as you mentioned. So what will be this? You have a vector space for the associated to the inner mechanical system, and you have another Hilbert space associated to the outer dynamical system, mechanical system, and what you expect is a map from this initial Hilbert space to this final Hilbert space. And this map is a linear map that says this vector goes to this vector. This excited state goes to this excited state. And that's the idea. And the way is physicists will say, I'm doing this through path integral. But the mathematician says, okay, I have a linear map. I don't care about the way you construct this linear map, even though the way you are constructing this linear map is not very well defined, is not very precise. At the end of the day, you do some calculations and you get a linear map. That's my part of the recipe. You give me a linear map. And this is a topological quantum field theory, this recipe. You say, okay, forget about I understand the physical intuition behind these kind of ideas, but I focus on the mathematical structure. And the mathematical structure is the recipe that says to every manifold I associate a vector space, and to every Bordism I associate a linear map. And that's the rule. That's the rule. And you say, okay, what are the possible rules? This rule, if I say this word, the precise word in mathematics is a functor. It's a functor because it's something that sends some kind of structure into some kind of structure. Okay, so you have these possible functors, and the key problem is what possible functors can I construct? What are all the possible functors, all the possible topological quantum field theories that I can construct? It's true that mathematicians, we don't have too many quantum field theories, because the typical quantum field theories that we have are precisely the quantum field theories that are created through physics. So it's like, okay, I have this mechanical system. I quantize this mechanical system as in reality, as a physicist will say. I'm quantizing this mechanical system as a physicist will say. And then I'm getting this linear map, which is the path integral that a physicist will say. But you can say, okay, you could say, okay, what are the topological quantum field theories that I can construct with no physical intuition, with no physical mechanical system underlying, and what are they useful for? Why are they useful? And for instance, maybe you say, okay, I'm creating this functor, this rule, through these ideas, and after creating this rule and saying, okay, I have this rule is very clear, is well defined. Is there a mechanical system underlying this construction for which this functor is the quantum counterpart? So you can ask in the other way around. Okay, I was able to define this very precise mathematical structure, and now I want to understand if there exists a mechanical system so that the physicist recipe gives my mathematical framework.
Okay, how do you go about validating that?
So in this paper, what I did was precisely to try to understand what are the possible quantum field theories that arise. That's the idea. And I actually, my main focus in this paper was precisely to understand these quantum field theories, not because of their physical intuition, but because of their mathematical application. And the key point is that there exists a crucial application of topological quantum field theories to algebraic topology. And let me explain what is algebraic topology. The idea of algebraic topology is geometry is very complicated. Being able to distinguish between different manifolds is very complicated. So, for instance, if you give me a surface, a random surface, it's not super easy to me to distinguish if these two surfaces are the same or not. So I would like to be able to assign some algebraic quantities, typically numbers or polynomials, to these manifolds, so that I say, okay, if I have this surface, I compute this number. If I have two surfaces and the numbers are not the same, the surfaces themselves cannot be the same.
And when we say the same in this context, are we really talking about identical surfaces in the strict sense of that word, or are we talking about some, let's say, derivatives of those surfaces being the same? Like, I think if we're talking about invariants in a second, we have like the Euler invariant, for example, and that encodes some information about a surface, but not necessarily all of the information. Are we talking about some form of strict equivalence here, or are we more loose in that definition?
I'm talking about the isomorphism idea. And isomorphism means I have two surfaces and I would like a map from the initial surface to the final surface that is invertible. That will be the idea.
Mm-hmm.
So I have to be able to translate every possible point in my initial surface to every possible point in the final surface. This is, mathematicians will say that we are thinking about manifolds up to diffeomorphism, which means a map from one to the other that is smooth, is differentiable, and has inverse, and the inverse is also smooth. That will be the idea.
Mm-hmm.
I'm trying to say, okay, does there exist an isomorphism between them? That's the way I want to understand this geometry.
Mm-hmm. Okay. And how is that necessary, or how does that relate then back again to the concept of topological quantum field theories? Like, what is this, let's say, the attributes of this mapping that we have, the fact that it's differentiable, for example, how does that play a role in considering these different quantum field theories? How does the necessary condition for this existence of that kind of map relate to the concepts we were discussing before?
That's a very good question. So let me explain a very particular example of invariant. A very particular but very visual invariant is the so-called genus of a surface. So you have a surface, and what happens is that a surface is essentially either the sphere or the torus, so a donut, or a torus with several holes inside.
Mm-hmm.
So, and that you can classify surfaces, and it turns out that these are all the possible surfaces. So you have a natural invariant associated to a surface, which is the number of holes inside my surface. So a sphere has zero genus. This invariant is called the genus. The sphere has zero genus because it has no holes. The torus has genus 1 because it has one hole. The donut, when you glue two donuts together, you will get something that has genus 2 because it has two holes, and so on and so forth. So you have an invariant, which is the genus, the number of holes inside my surface. And you say, okay, this is cool because now I'm able to distinguish between two different surfaces by looking at the genus. You give me a surface, I compute the genus, and I say, okay, if the genus is the same, then they are the same manifold. Otherwise, they are different manifolds. Cool. The problem is that when you look at higher dimensional manifolds, this is much more complicated. It's not that simple. If you want to distinguish between three manifolds or four manifolds, and you want to understand if these four manifolds are isomorphic or not, it's not that simple as computing some numbers. There are more invariants, and the problem is that computing these invariants is super complicated. So typically, it's related to solving some partial differential equations and counting the number of solutions to these partial differential equations. Or you are saying, okay, I want to understand some subtle invariant associated to this manifold that I'm not able to compute precisely. So computing this kind of invariants, first of all, typically they are not numbers, are something much more complicated, like polynomials or even vector spaces. And you want to be able to compute these invariants, because even though you can define them in particular examples, if you give me a random four-dimensional manifold, I wouldn't be able to give you a precise formula of this invariant for this manifold. And this is a difficult problem because these higher dimensional spaces arise naturally in very different ways. For instance, they arise naturally when you want to understand some physical phenomena, like I want to understand this PDE associated to particle physics, and the solution of this PDE, it turns out that this PDE has not unique solution. It has actually a lot of solutions, and actually the solutions are a lot in the sense that they form a geometric space. They form a manifold.
Mm-hmm.
I have a manifold, and the points of this manifold, each point of this manifold is a solution of a PDE. And I would like to understand how is the structure of this manifold of solutions of this PDE. And I would like to be able to compute some kind of invariance, because I want to say, okay, the solutions to these systems and the solution to this system are different or not. So they are the same. Are they the same system or not? And what you do is you apply topological quantum field theory to compute these invariants. So the idea is you can use this technique, this idea coming from theoretical physics, to give a precise rule, a recipe for computing these invariants to higher dimensional manifolds. And that's the idea.
How come you say to higher dimensional manifolds? So I get the point that we have, let's say, a quantization of the subfields that we were discussing before, or the manifolds that describe the system. We would like to compute some invariant, and for a classical manifold, that would be, well, not straightforward necessarily, but the concept of what we're trying to do would be more straightforward. Now we're somehow quantizing the manifolds themselves, and consequently, we also have to potentially quantize the invariant. How does a higher dimensionality relate to this? So yeah, that's the point I'm struggling with now.
So the point is that what is going on is that understanding the invariant itself, it's something that is static. So you have a manifold and you compute the invariant associated to this manifold. And this is a super static picture. You want to understand not only what happens with the invariant that I'm associated to this manifold, I will also try to understand what is going on with this invariant when I'm evolving my manifold into a different manifold. And that's the idea of a Bordism.
And can the manifold evolve in such a way that the invariant would change over time?
Yeah.
I take that it would. Yeah. Okay. How come? Because that to me sounds a bit counterintuitive. Like if we have this mapping now that we're interested in, and that one needs to be differentiable and well, I guess bijective or linear. Doesn't that put some constraints on these invariants not changing, or that seems to not be the case?
That's a great question. Let me explain this in detail. Maybe you can scroll down in the paper, because there is a picture there that I can use to explain this. That one, exactly. That one.
Okay, great.
Okay, so the idea is, let's suppose that we want to quantize the genus, because it's our super simple invariant. So we want to quantize the genus of a surface, and the point is, okay, let me look at this surface. This surface is a donut that has G holes. So I want to compute G, the number G. I want to compute this number G. Cool. How can I compute this number G? So the idea is, if you look at the whole surface, which is a surface with G holes, as a Bordism, this is a Bordism between the empty set and the empty set, because it has no boundary. That's the idea. This manifold, this surface, has no boundary at all. So at the left hand side of this picture, I have nothing. So it's the empty set, the empty manifold, and at the right of my surface, I have the empty set. So I can understand this surface as a Bordism between the empty set and the empty set. And let's quantize this surface, this Bordism. So the idea is, okay, let's look at the rule. The rule says, to the initial boundary, which is the empty set, I have to associate a vector space. Since I'm considering the ground state, the ground possible physical system, the simplest physical system, the Hilbert space that I'm associating is just the complex numbers, the simplest possible vector space I can consider. And the same for the second boundary. I have the empty set, so I'm associating the complex number as vector space. And I have a map, a linear map from the first copy of complex numbers to the second copy of complex numbers. So I have a linear map between C and C, which is a linear map between two vector spaces of dimension 1. So it's a 1 times 1 matrix. And this 1 times 1 matrix is one number. And this number, I want that this number is the genus. That will be great. If I manage to construct some rule such that when I have the genus G surface, I assign to the left boundary the empty set. I assign to the right boundary the empty set. I quantize these empty sets so that I get C and C, complex numbers and complex numbers. And the linear map that I get through them, this linear map will be physically the path integral through this genus G surface. And I want that the result of this path integral through my genus G surface to be G. And in that case, I will say, okay, I managed to quantize this invariant because I managed to assign to every possible surface, closed surface, a linear map, and this linear map is precisely multiplying by my invariant. And you may say, okay, Angel, that's fine, but you are overcomplicating something that is super simple to understand, because you will say, okay, what the genus is something that can be computed by looking to the surface. But I say, okay, now suppose that you want to understand a super higher dimensional manifold, like a manifold of dimension 10, and you say, okay, I have my manifold of dimension 10. This manifold of dimension 10 has no boundary, so it's a Bordism between the empty set and the empty set. I quantize the empty set, so I get complex numbers and complex numbers, and I get a linear map. And suppose that this linear map, which is a number, because it's a 1 times 1 matrix, is the invariant, the super complicated invariant that I want to compute. In that case, you will say that you manage to quantize this invariant. And why is this useful? So let's look at this picture again. So the idea in this picture is that instead of looking at the surface, the genus G surface, as a single surface, I chopped it into several different surfaces that are simpler. And I cut it into a disk, the disk that is on the left-hand side, this D. I also consider this like a tube that has a hole inside. I call this L, and since I have G holes, I can cut my surface into G of these objects, and then I get a disk in the other way around at the end. And the point is, okay, my invariant, that in this case is the genus, and it's very simple. Now it turns out that this linear map from complex vector space, from complex numbers to complex numbers, I have decomposed this linear map into the composition of several linear maps, because now D is a Bordism between the empty set and the circle. So when I'm quantizing this, I'm assigning to the empty set the complex numbers, but to the circle, I'm assigning some vector space. Let's call this V. So I'm assigning some vector space V to the right boundary, and then I look at L, and L, when I'm quantizing L, I'm assigning to the left boundary some vector space V, the same vector space, and to the right boundary the same vector space V. And I'm doing this G times, and at the end I got a map from B to complex numbers. So my initial map from complex numbers to complex numbers, that was very complicated because it was related to a very complicated invariant, I have split it into a composition of simpler maps, because I have composed as I have a map from C to V, I have a map from B to B G times, and then I have a map from V to complex numbers. So that if I'm able to understand three linear maps, and these three linear maps are independent of the surface I want to consider. The three linear maps are the linear map associated to the disk D, the linear map associated to the Bordism L, and the linear map associated to the disk D dash. Then, if I understand these three linear maps, I'm able to compute my invariant for every possible surface, because the only thing that I have to do is to say, okay, I'm computing this guy as many times as needed, and this guy. So that now let's look at the higher dimensional setting. In a super higher dimensional setting, I have a super complicated manifold that I don't understand, but I managed to chop this super complicated manifold into simpler pieces. And this is something that geometers try to do, try to understand, okay, how can I chop this super complicated manifold into super simple pieces? And the idea is, if you are able to understand how to quantize each of these simple pieces, the topological quantum field theory gives you a recipe to glue them to compute the composition of these linear maps, and then you get the linear map that you are looking, and this linear map is precisely multiplication by the variant that you were not able to compute. So you are able to compute the super complicated invariant by computing something different, something slightly more complicated, but for simpler manifolds. Manifolds that you can understand because are super simple manifolds. And that's the idea. That will give you a recipe for computing this invariant. You will say, okay, I have a manifold that is a tube like this, glue with a tube like this, and then I glue another tube like this, and then I do this twist. Okay, I compute the linear map associated to this, the linear map associated to this. I glue them together, and then I get my invariant. That's the key idea of topological quantum field theories, and how topological quantum field theories are useful for computing algebraic invariants.
Okay, a couple of follow-up questions. First of all, is this what we're referring to when we say that we're discretizing the invariant? That we're splitting it up in this way, or is that term referring to something else?
So when I'm saying that we are quantizing the invariant, what I'm saying is precisely I'm constructing a topological quantum field theory doing exactly this, being able to chop this invariant into simpler pieces. That's the idea.
Okay, and the complexity in these kind of situations, does that mainly arise from the higher dimensionality of these more complex manifolds? Because I guess in that case, it looks to me, based on the example that we looked at now, that in doing this chopping up of the surface, you introduce the price you pay, so to speak, is that you're introducing higher dimensionality in the subparts of splitting the surface. And if the dimensionality is the key problem, I don't see that this would be particularly useful. I take it that the dimensionality is not necessarily the key problem, given that this has some bearing on the field. So is the problem more related to the complexity of the manifolds that we're considering in these higher dimensional spaces, and that this then becomes useful because, well, we're able to pay the price of a higher dimensionality still if we chop them up, but nevertheless, we get around the complexity of treating this entire thing at once.
Exactly. So that's a very good question. That's the idea. The idea is higher dimensional manifolds can be created by gluing simpler pieces in a very complicated way. So the problem in higher dimensional manifolds is the complexity of the manifold. I completely agree with you. But I have also to point out that even though you are splitting your complicated higher dimensional manifolds into simpler pieces, and you say, okay, this is something that is more complicated because now you have a rule. Recall that at the end of the day, the topological quantum field theory says, even though your manifold was a manifold that has some geometric structure, at the end of the day, you have to deal with a vector space. And dealing with vector spaces is something simple. It's first course on linear algebra. So it's that you are converting a very complicated geometric problem into a linear algebra problem. Even though the linear algebra, okay, maybe these matrices are very, very large matrices, and maybe computing them takes some time with a computer, is something that is doable. But computing with manifolds, with higher dimensional manifolds, is not that simple. So let me explain this in simple terms in the case of three-dimensional manifolds. In the case of three-dimensional manifolds, it turns out that every three manifold every three-dimensional manifold can be understood in a very precise way as combining 8 different possible manifolds. And these 8 possible different manifolds are known as the Thurston geometries. Because
Okay.
Thurston was the first guy that conjectured that these 8 manifolds, 8 geometries, were the only geometries that were needed. And some years ago, mathematicians managed to say, okay, that's right. Combining these 8 possible spaces, I can get every possible three-dimensional manifold. That's great because even though there are infinitely many different three-dimensional manifolds, and if you give me, okay, compute this invariant to this three manifold, and this manifold is super complicated, I can say, okay, take this manifold, decompose it as simple pieces, and a combination of these 8 possible geometries, and then compute the TQFT for these 8 possible geometries. So that decompose this as a Bordism, like in this picture, in figure 1. And you say, okay, compute the TQFT associated to these 8 possible geometries. So you get 8 possible linear maps, and that's all that you need. With these 8 possible linear maps, now you can glue them together and compute any invariant that you want for any possible manifold. That's the idea. You are reducing the complexity of the manifold into the complexity of the functor.
Okay. And then, given that we only have a few minutes left, the last thing I would ask you to do is if we could then tie this back to the main question of this paper that you have here formulated, what is it exactly that we're looking for? So if we read this, given an invariant, does there exist a TQFT Z from this set to this set such that this equality holds here? Would you mind just giving a very short overview now? I granted that we don't have much time to discuss this anymore, but would you mind just describing what is the question that we're trying to answer here regarding the existence of these structures?
That's a very good question, and the solution is the question is, as I was mentioning during the whole interview, the idea is I have an invariant. This invariant is very complicated. This is the he there in the question in the paper, that one exactly. And I have this invariant, and I'm asking, can I construct this topological quantum field theory such that when I'm considering a manifold that is a Bordism between the empty set and the empty set, the 1 times 1 matrix that I'm associated to this Bordism is the invariant that I want, and this is the equation that is in the second line, at the beginning of the second line, that the invariant associated to this manifold that I'm calling W is the TQFT set associated to W, which is a linear map from complex numbers to complex numbers, and a simple way of getting the unique entry of the matrix is by evaluating this linear map in 1. So it's this linear map evaluated in 1. So the problem is, if you give me an invariant, can I construct this dynamical picture of the invariant such that my invariant can be constructed through this? So that if I have this functor, then I can do the same trick, and I can decompose my manifold into simpler pieces and compute invariant.
How much previous work has been done on this? Is this a very new way of approaching the problem, or is it something that's quite mature?
Actually, it's quite mature. So this question, I mean, I think that this question has never been formulated in this precise way, but looking for TQFTs computing particular invariants is something that has been done for the last 40 years. So we have plenty of examples of TQFTs computing particular invariants. That's true. But I think this is the first paper in which they say, okay, let's look at this problem in a different way. Can I characterize the invariants for which I have this device, this technique to compute them? And I think this is the first paper in which this question arises. Like I'm going to look at this problem in a completely different way.
Okay, great. In terms of the next step for you, given the research that you've done now and things you would like to look at going forward, is there anything you found here, like any new, let's say, directions to take this research that you would like to pursue?
Yeah, actually, in this paper, I managed to understand some cases in almost completely. So, for instance, I was able to understand the problem of computing invariants for two-dimensional manifolds completely. So, if you,
Mhm.
I kind of describe a recipe that says, if you give me an invariant for surfaces, can I be, can I do I have a precise procedure to say yes or no, there exists a TQFT or not? So I managed to do this, so that's cool. First future work, can I extend this kind of techniques for higher dimensional manifolds, three-dimensional manifolds, four-dimensional manifolds? And the second open problem that arises from here is that this question is particularly applied to a very particular invariant that arises from theoretical physics, which is called the Poincare polynomial of the character variety, some random word which is an invariant associated to a manifold. And in this
Mhm.
paper, I actually proved that for this invariant, there does not exist a topological quantum field theory computing this invariant. I
Mhm.
managed to compute that there exists something slightly slightly weaker, which is called a lax monoidal topological quantum field theory.
Mhm.
And I proved both things. The first thing I proved that there exists no such a TQFT, and this this is the key point of this paper. And the second part, which is a part that I did in a previous paper, I proved that there exists a lax monoidal TQFT computing this invariant. So in this paper, I'm solving the question of, can I do this better? And the answer is no. In this paper, I say the answer is no. But there are some open questions here. The problem is that
Mhm.
this lax monoidal TQFT that I managed to construct for computing this invariant that is super complicated, uh, is not monoidal, is something called lax monoidal, and this means that the vector spaces that I'm associated to my manifolds are no longer finite dimensional. If the
Mhm.
TQFT is monoidal, there is no lax in the name, you can prove that the vector spaces that you have to associate are finite dimensional, and that's fine. So you are
Mhm.
dealing with linear algebra. But here, the vector spaces that you get are infinitely dimensional. So it's not that simple at all. It's not as that simple as writing a matrix, and that's all, because your matrix is infinite. But in some particular cases, I saw that this invariant, even though these linear maps are infinite matrices, there exists a finite dimensional invariant subspace. So even
Mhm.
though the matrices associated to from the TQFT are super big, there exists a small part of the matrices that is all the information that you need, because this
Mhm.
vector space is invariant when I'm gluing new inputs to my manifold. So this
Mhm.
vector space is says a core for this invariant. And what I say here is there a way, the new open problem is there a way of saying, even though this invariant is not quantizable through a genuine TQFT, it's only quantizable through a lax monoidal TQFT, can I still find this invariant subspace that make my life easy, in the sense that even though the functor is not that good, as good as in the previous case, I can work with it as it was. Can I do this
Mhm.
for a general invariant? And this is an open problem.
Mhm. Okay, great. Okay, we're over time, but for anyone who's interested in looking at more details of the paper that you published, I'm going to put a link to it in the description so that people can check it out. I would like to thank you very much for taking the time to explain this. This was super interesting for me, and yeah, I'm really happy we got to do this. So thanks.
Thank you very much for your interest. Thank you very much for your time and your effort. And of course, if you have any questions or anybody has any question, don't hesitate to drop me a line. My email is written in the paper, so you can write me as many times as you want. Thank you very much for the interview.